Hello everyone. Hey, this video going to show you another example for axial loading information and for textbook example 9.3. Yeah, this example needs some more explanation. Okay. This problem is like this: is a reed beam raised on the two posts. Okay, the being AB is here, and it's placed based on these two posts. Okay, AC post and BD post. And the AC is made of by steel. Okay, AC is made of steel, and the cross section area is 20. Cross section, oh, sorry, the diameter is 20 millimeter. It is made of aluminum and diameter 40 millimeter. Determine the displacement at point F. F is here. Okay. And then we apply the external loading 90 kilonewton on this beam. Okay, it's point down. Okay, you want to calculate deformation of heat deformation at this F point. Okay, so this problem, okay, this really needs some explanation. Okay, so we need to draw some code diagram. Okay, let me draw the free body diagram of this problem. Okay, we draw the free body diagram of the beam AB. Okay, we draw a free body diagram over here and draw this beam. It's not thick. It's thick. Okay, it's A here and B here. We have external loading 90 kilonewton. Maybe I should 90 kilonewton here. And he said the position of this force is 200 millimeter from the A and 400 millimeter to B. Okay, it's millimeter. Okay, just okay. Okay, so when we apply the 90 kilonewton, push this point down, the 90 kilonewton to under this beam. Okay, this beam. Okay, this beam will feel the supporting force from AC and BD. Okay, this beam will feel a force from AC and BD, because in this course everything is static. Okay, so this beam, after this external loading, the beam and the AB beam is also static. So there must be some force comes from the post. There must be force comes from the post to make the beam static. So I call this A here. I just call it FAC. So maybe I just call it NAC. Okay. Or maybe I just the direction. I call it NCA, C to A. Okay, C to A. Okay, C to A. Okay, and this is D to B. Okay, so there must be these two forces. Okay, to balance the external force here to make this beam static. Okay, and okay, so where this formation comes from? He said you want to calculate the formation of the point F. Where is the deformation comes from? Where does deformation comes from? So okay, so okay, because we have the force from this post. This is a force from the post. So at the same time, there's a reaction force. There's a reaction force. The reaction force. There must be a reaction force. Be careful. There must be a reaction force. Reverse, I call it NAC. Okay, there's a reaction force here. NBD. Okay, this is action and reaction. Okay, so this is action reaction pair. Okay, this is action and this is the reaction. This color is reaction. We had force from C to A, but at the same time we have reaction force from A to C. Okay, we have force from D to B, so at the same time we have reaction force from B to D. So the NAC, for this force NAC and NBD, they will cause the deformation of the bar. Okay, do you understand that? Okay, so let me draw another diagram. So this NAC, so this is AC bar. This AC bar. This is AC bar. Here and here is BD bar. Okay, so this reaction force NAC and NBD will compress the AC bar and BD bar. Okay, and this must be NAC here because everything is static. So this reaction force will compress the AC bar and BD bar. Okay, that's cause a deformation. That will cause a deformation. And these three members are connect together. So the deformation of DF, the deformation at the F, the deformation at F is connecting to connecting deformation. How to describe the deformation at F? Okay, relates to the deformation at deformation of AC and BD. Because these three members are connect to each other, okay, or attached to each other. So the deformation at AC and BD must be has something to do with deformation at the point C. So that's the logic of this problem. So what's how to solve the problem? How to get the deformation at C? So first of all, we need to know the deformation of the AC bar and BD bar. So when you calculate deformation at AC bar and BD bar, and then we will use the geometry relationship between the A, B, C, D, F, and then find out deformation of the F. Okay. Okay, so the most key issue is find the deformation of AC bar and BD bar. So what's the formula for the deformation? Okay, don't forget it. In axial loading, the deformation is calculated by NL divided by EA. Okay, so do we know the L? Yeah, we have L. We have LAC. LAC and LBD is the same thing. Okay, 300 millimeter. And do we have the same modulus? Elastic modulus? No, we don't have the same modulus because it said AC is made of by steel. BD is made of by aluminum. So it's different material, they must have different modulus. So it gives you the modulus, so you don't have to check again. So AC is steel, so it's 200 gigapart, and BD is 70 gigapart. Okay. And do we have the same cross-section area? Uh, no, because it say AC has a diameter of 20 millimeter, BD has a diameter of 40 millimeters, so they have different cross-section area. So be careful. Okay, AAC is equal to, it's give you a diameter, so it's pi over 4 and 20 10 to the power minus 3 square. Okay, fine. Okay, that's right. Okay. So I just right now I don't want to calculate the value. So AAC, so ABD is pi over 4 and 40 times 10 to the power minus 3 millimeters squared. Okay, so we have all the same. I think we have all the information. Okay, I think all the information. We have LEA, we all have information. And the only thing we don't know is the N normal force. Normal force NAC and NBD. So how to get NAC and NBD? Yeah, we have to back to this the equilibrium of the beam AB. Okay, the beam AB here, it gives you a lot of information. So you can use the rigid body equilibrium of the beam AB to find out the NAC and NBD. Right? Okay. So once again, we have to use the rigid body equilibrium. Okay, so we apply rigid body equilibrium here. So the rigid body equilibrium. So beam AB, we have rigid body equilibrium. Rigid body EQ, rigid body equilibrium. Okay, that means the total force equal to 0 and total moment also equal to 0. Okay, and total force we only consider the vertical force because in the system right now we only have the vertical force. So Summation Fy equal to 0. Okay, and we consider NCA and NDB. Okay, this because this is a two force acting on the beam AB. Okay, so we have NCA point up, so NCA point up, and we have 90 kilonewton point down, and we have the DB point up, and DB point up, and equal to 0. Okay, so NCA plus NDB is equal to 90. Yeah, right now we still cannot solve the equation. Okay, and the next thing is the total moment is equal to 0, and we choose the reference point. Okay, we choose A as the reference point. Okay, so we don't have consider of any force here, and we have 90 kilonewton point down, and it's clockwise, so it's minus 90 times 200 millimeter. And we have the force here, NDB here. DB will create a counterclockwise rotation, so it will become a positive counterclockwise rotation, 200 and NDB, and it's times the for 600 equal to 0. So based on this, we will have the NDB. And be careful, the unit here. Here we use the kilonewton times the millimeter times the millimeter. So here is also millimeter. So the NDB here, the unit is kilonewton. So what's the kilonewton here? Let me check my notes. Wait a second. Hey, what's the value? What's the value? Okay, let me see. What's the value here? Oh, 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 oh. Mhm. Okay. Mhm. Okay, so I think you have I think the NDB is let me see. NDB will equal to, let me check my equation. Yeah, equation is right. Oh, NDB I think it's 30. Okay, you'll find that NDB is 30 and it's kilonewton. Okay, and so we'll have the NCA is equal to 60 and kilonewton. Okay. So we have NCA and NDB. So at the same time, so we will have NAC and NBD. Right? Just take a negative sign. Okay. So we start from, okay, we found delta AC. Okay, so what we are going to do is we put the NAC in there. NAC is negative, so negative NCA. So it's minus 60 times 10 to the power 3. Okay. And LAC, I think we just use 300 millimeter. Okay, and cross-section area AC is pi over 420 times 10 to the power minus 3 square. Sorry, this is, I should put the G, for- I should put elastic modulus first, one times in, and well, pi, yeah, square. Mm-hmm. Okay. So let's see what's the value here. Let me see my answers. Oh, sorry, nothing. Let me see my equation. So okay, if we use the engineering calculator, I think the answer will be hmm, really, really, really. Okay, so if you calculate right, I think the answer 286 times 10 to the power minus 6 meter. Actually, is equal to minus 0.286 millimeter. And negative, that means it's compression. When negative is compression. Okay, so okay, and that's the first thing. Okay, the next thing is okay. So next thing is BD delta BD. Okay, the only thing we need to change is length is the same, 300 millimeter, and the BD so negative sign here. So it's minus 30 times 10 to the power 3. And the giga is 70 gigapascal, so 70 times 10 to the power 9. And the next thing is the cross-section area pi over 4 and 40 times 10 to the power minus 3 square. Okay, so if you are using a calculator, right, I just give you the answer directly, so just try yourself. So it's minus 102 times 10 to the power minus 6 millimeter. Actually, it's about minus 0.102 millimeter. Okay, negative means just compressing point down. Okay, we have the deformation of AC and BD. Okay, but that's not our goal. Our goal is to find the deformation of point F. So and we know the deformation at F relate to the deformation at AC and BD because these three members are connected together. So there must be geometry relationship between these three members. Okay, so the final part. So how do we finish? So let's finish the final part. And I don't have space here, so just erase here. So the final part I'm going to do is okay. So final part is we have the deformation AC and deformation BD. Okay, so let's draw a diagram. So you need a diagram to show the final part. So we have deformation of AC, deformation of BD. So it's compression. So it's a compression here, here. So we have deformation here. We have deformation here, deformation AC, and deformation BD. Deformation AC, what's the value for deformation AC? 0.286. Yeah, right now we don't need a negative sign here. We just know the magnitude, want to know the magnitude. So, okay, so 0.286. And what deformation at BD? 0.102. It's millimeter, units is millimeter. Okay, so they connect to each other. Okay, so we treat the bar as a straight line, and here is point F. Okay, so okay, I should say maybe here's better. Okay, 0.142 and 0.286. Yeah, I need to read. Yeah, maybe it's not probable to show a number here. Okay, let's see. Before deformation, this AFB, before deformation, AFB is at the straight line. Okay, that's the before before deformation. Yeah, but after deformation, yeah, we had deformation on AC and BD, AC and BD. This is after deformation. So after deformation, because they connect to each other, so there's I think they are straight line. Okay, so here is after deformation. Can you imagine that? Before deformation, ACB is at the same plane. After deformation, we have the deformation on the AC part, and the deformation on BD part. And because these three members connect to each other, we can treat this CD maybe this deformation. I was going to treat this as a straight line because of this small deformation. We just treat this as straight line. Okay, and also that's why there's a deformation here. That's why this problem tell you to calculate deformation at point F, because after deformation the F prime it will become here, and this is a deformation at the point FF. Deformation. So actually, the deformation of point F means to calculate the length of F prime. That's the deformation at F. Actually, you want this part want to calculate F prime. Okay. So how to calculate F prime based on this geometry? Yeah, we have the geometry here, and this distance here is it's 200 maybe. It's here is 200. Here is 400. Okay, 400, 200. Okay, so how to find the F prime, the deformation upon F? How to find the F prime? Okay, so we just okay. If we cut here, so let's cut here, and here we have the 0.102, right? 0.102. So you know what's the distance here? How to solve that? Okay, so let me draw the other skin. I draw the final right triangle. Yeah. Okay. Here is 0.286 minus 0.102 is equal to what? What's the value? 0.184. 0.184. And here is 200. Here is 400. So 400 to the 600 is equal to the deformation at F we don't know. Oh, sorry, actually it's not. I just call it called delta 1. Okay, delta, let's call it delta 1. Okay, so delta 1 here, delta 1, and here is 0.184. So you will get a delta 1. What's the delta 1? Okay, delta 1 is 0.184, 0.184 times 400 divided by 600. So it's equal to 0.1227. So the deformation of F, so F prime, finally the F prime, the value is just 0.102 plus 0.1227. So what's the value? 0.1227 plus 0.102. So it's 0.2247 millimeter. Okay, so it's very close to the answer from the textbook. Yet, for this part, F prime, the deformation at point F is actually equal to 0.2247 millimeter. So actually, in this problem, okay, it just used the deformation formula to calculate the NC deformation at AC bar and BD bar, or BD AC post and BD post. And then because these three members connect to each other, so the deformation at point F has a relation to the deformation at AC and deformation at the BD. So you need to use the geometry information to calculate the deformation of F. So it's F prime. So yeah, so the geometry is really important in this course. Okay, so don't forget the some basic geometry relation or geometry connection between the simple shape. Okay, similar right triangle, right? Okay, so I just start a video here. Okay, so I just start video here and see you in another video. Bye bye. Ooh.